Good afternoon, everyone. Thank you for joining us for today's second session of the day 3, STTP on IoT and Advanced Power Electronics Application in Smart Grid, jointly sponsored by AICTE and KKWIEER Engineering Education and Research, Nashik. My name is Dr. Mohan Thakre and I am working as Assistant Professor at KKWIEER Institute of Engineering Education and Research Center. I welcome you all to STTP on behalf of Organizing Committee. Today we are presenting power quality issues in on-board grid charging for electrical vehicle, presented by Professor Dr. Mohan V. Aware sir. I take the opportunity to introduce Dr. Mohan V. Aware sir. Dr. Mohan V. Aware received the BE degree in electrical engineering from the College of Engineering, Amravati in 1980 and MTech degree in power apparatus and system from IIT Bombay in 1982. PhD from Nagpur University in 2002. He was design officer with Crompton Greaves Limited, Nashik, India from 1982 to 1989 and 1989 to 1991. He was development engineer with the Nippon Derno Ispat Limited, Nagpur. He is currently professor with the Department of Electrical Engineering, Vishwesvaraya National Institute of Technology, Nagpur. His current research interests include the multiphase electrical drive, fractional order controller, and power electronics, also high voltage engineering. Dr. Aware is Commonwealth Academic Fellow. He was recipient of Biman Bihari Sen IIT Award. He is an energy auditor, also senior member of IEEE USA. He has guided more than 10 PhD scholars and around 30 PG projects. He has more than 200 SCI publications with the citation of around 700 in various reputed journals. He has also completed many projects sponsored by DST, MHRD, CDAC, and many industries. I welcome you, sir. Now I request Dr. Mohan V. Aware sir to start the session.
Thank you, Mohan, for introducing me.
Thank you, sir.
Okay. Am I audible to all of you?
Yes,
Hello.
sir. Yes, sir.
Okay. Good afternoon to all of you. So I welcome you to my session, which is a part of this STTP IoT and Advanced Power Electronics application in Smart Grid. This is a very relevant topic, and I find that my interface in this particular arena is related to a electrical vehicle when they are connected to the grid for charging. When you do this one, we have some issues which are related to the power quality and how to deal with that one. What are the ways how we can make basic design in electrical propulsion system and also in charging, so that we should able to get best of the possible thing when you get these electrical vehicles as one of the considered future load on power system. So considering that part, I will just make some introduction for all of you related to my presentation. Of course, we all know that in specific area we need to investigate more detail about its real impact when we think about initially that it's going to be easy task for us to make an electrical vehicles to be used with in our present transportation system. While doing so, we definitely have many problems which are associated, because whatever charge we need to store in the battery in place of gasoline or petrol, we have to take this charge from our grid. And you could see that there are various grid stations which have been erected, and you could see that these grid connected chargers which are being there are causing certain trouble to the grid, and that is what we are going to see. So that is one of the important challenge which we are going to face. So we are interested to find out what could be solution. Then we will focus basically, because the topic is quite broad, so I would like to focus only to the integrated onboard battery chargers. There's some very interesting thing which I will be presenting to you, because in integrated onboard battery chargers will be bit convenient and also useful in electrical vehicle. But when you try to do this one, we are going to have some issues. Those issues which we have to understand and try to overcome. So present state of art in the research I will be just introducing, because there are many people who have contributed in this particular part, and it is growing furthermore. Then there is something like electrical vehicles which are been running with certain control technique. We are not going to talk about all the things, but we are going to specifically say that which could get you issues which are crop up while making these integrated onboard battery chargers. And then of course, when you try to make a charging operation, that time, what could be the way you have to look at with the problem which are going to be associated, and we have to overcome. So this is really a domain wherein the power quality with the grid is going to be an issue. We'll see that part in my presentation, or we can discuss all the questions at the end of my session. So let me present now this particular topic to you. You could see here, India gets very first electric vehicle charging station in Nagpur, 20th November 2017. This is at the airport. There is an electrical station for charging. This is a charger for our Ola cabs which are there. And you could see here a very nicely built Ola cab charging station at another place also. So this is a beginning in Nagpur. As far as I know, it is in 2017. And there are many Ola cabs which are running with electrical power. Considering all these kind of growth which takes place, there is something which is projected in the future. You could see here a lot of combinations will be there, like from bicycles to a bus or trucks, and contribution by India by 2030 will be of such a huge thing that will be going to be within 10 years, next 10 years. So for all these particular electrical vehicles from bus to cycle, you would like to have chargers, and we will be going to put all this power, if it is not from solar but through the grid, then you have some trouble while getting this grid connect to the charging operation. So many things are going to happen, because that's a mission of our country. I will just put something as a background. You could see here the cost structure of electrical vehicle, in which almost battery pack will be having 35 to 50% cost, and electrical drive line, that is around 8 to 20%. Out of that, you will find that 30 to 43% contributed by the electric motor, then 30 to 47 is the range for inverter, and other thing will be just control unit, transmission, onboard charger, and all that one. However, this component which is been going to be here will be making more and more impact in complete costing, because this is going to be one of the critical component which is taken care in design. So what we are going to make by looking into this area is like, we should have a increased battery life and its capacity up Of course, whenever we talk about the charging, we need to see that battery life has something very important kind of consideration when we invest into electrical vehicle. Another is a time constraint for the charging. As fast as we can charge, that is the best part, but batteries will have its own time constraint. And also we have a charging system which is going to cope up with that particular load. So we have to match them properly so that we will be able to build a complete integrated system for charging. Obviously, it should be efficient, it should be lightweight, it should be more reliable, number of components should be less. All these things will be an essential part of any electrical system design. So considering this one, we will be just looking for a electrical machine that goes into electrical vehicle. And you could see this, that 1884 to 2016, there's some data which is there, that PMSM is contributing much higher. Next to that is induction motor. DC motors are there to some extent. Then SM, SRM, all these synchronous motor, SRM motors which are there, they are very less in number. But you see next figure, in the last 20 years, what has happened? PMSM is high and induction motor is also growing. DC motor is going down and other motor are also taking shape in contributing to this particular traction. So major component in our electrical vehicle is electrical motor, which should be robust, rugged, having less maintenance, and also it should be inexpensive. You could see that this criteria, whatever we have to get their induction motor is the best fit. So considering this part, PMSM has some advantages, but it is definitely costly, and also it has some critical component of magnets which are built out of rare earth. So we are interested to see that we should target induction motor in this particular arena of electrical vehicles. Let us come to battery charges. If we classify them, then you could see that it is based on power level, based on placement, also based on a direction of power flow, then concept of hardware reusability, and based on control. It's not control, it's contact. So basically you see that based on power level, three levels which are depicted as a standard SAE J1772 and type of power level 1, 2, 3, which are been categorized like onboard single phase, almost up to 2 kW. Charging time is quite large in this case. Level 2 chargers are onboard chargers, which could be either fed single phase or 3-phase supply, having almost range from 4 to 20 kW. Charging time is less. Level 3 is off-board 3-phase, having a capacity of 50 to 100 kW, and pretty fast charging is required. Considering this particular charging power levels, they are categorized. So there are certain constraints, and also an electrical vehicle which falls in certain categories of this power, we have to make use of our incoming supply to match that power demand so that we will be able to make a better charger. Similarly, placement is very vital for this charger. Charger could be inside the electrical vehicle or it could be outside also. So if it is outside off-board, we call it, and if it is inside, it's on-board. Then based on direction of power flow, unidirectional or bidirectional. When it is a grid connect and you are just charging, so it's a one-way direction. But if battery, which are also capable of supplying power to the grid, then it could be bidirectional. So such kind of possibility is there. V2G, I'm talking about bidirectional. And in that one, batteries could be utilized for generating the power for the grid. So under that circumstances, it could be a bidirectional power flow. Then there are, based on the concept of reusability, some of the hardware, as like I told you that vehicle to grid, when you do, then there is a possibility of an inverter that is used with the converter as well as inverter. Similarly, you can use in onboard integrated chargers something which can be considered as a reusability of a power electronic circuit. It is the same thing like converter can be used as an inverter. And so we will be able to manage both bidirectional power flow and we can build a better system. So based on the contact like conductive charging, inductive charging, that is another way of getting this particular charger to be connected to the electrical vehicle. Considering all this basic of classification, we are going to put forward a typically classification in terms of power level. Just now I told you that is like what I have got it from one of the paper that has indicated with the voltage level also very well specified for US as well as European Union. And here you can see that a power level which is up to 2 kW charging at home, that is a typical use. Charging at private or public outlets, it's up to 20, but here it is 4 to 8 kW. And timing is also given, which is shorter. And commercial or public, they have changed that one to 50 to 100 kW. So when the power level goes up, definitely incoming side, we will be going from single phase to 3-phase. Obvious reason is there when you go for the power levels very high. And obviously, what could be the major bottleneck? Well, every one of us is interested to charge our mobile fastest possible way, but we have to pay for it. Similarly, here also in electrical vehicle, if you find that you need to recharge, you can't wait for a longer than, let us say, hour or so, then it becomes a very typical kind of a issue that will not allow us to multiply electrical vehicle penetration in the market. So this charging time is one of the bottleneck, and definitely we are looking for the battery types which may be lithium-ion battery or a conventional batteries which are lead-acid battery at present. So I'm trying to get you a just overview of all basic electrical chargers which are being categorized, classified, and what could be the basically a limitation. Here is the basic idea how it looks like a battery charger arrangement in the electrical vehicle. You could see here it's a off-board charger. This off-board charger will have a supply which will be converted into DC and then given to battery for charging, battery which are there in the electrical vehicle, that will be charged. So this is an external unit. This This is an external unit. And then once it is disconnected, charging is over, then this battery will take over and this motor will be delivering the torque to the wheels. We will have DC to AC as an inverter in between. So this is basically off-board charger. You could see here onboard charger also. In onboard charger, what happened? We just take this part inside. So you find that your this AC to DC converter goes inside the vehicle, and there is a filter. F is for filter. So you have a supply here, and that supply will be connected to AC to DC inverter. AC to DC converter, and that is been given to the battery to charge, and from then battery will get you a torque through an inverter which is running a motor. So once it is with this charge, it will continue to run. So this is onboard charger. But what is integrated onboard charger? Here it's a very interesting thing to note. Here in this case, AC supply is here, then motor is here, then you find that on this side DC AC is written. It could be AC DC for the battery, and again back, that is DC to AC. You could see here what I mean to say is you get a supply from here through motor to this converter. This converter will convert this particular AC into DC, and then you disconnect this part. After charging is over, this battery will go and give this particular power to the motor. So again, the same converter here is used for DC to AC conversion. It means while charging, this converter works for converting AC to DC, and when you go for the propulsion mode, that time this will work as an inverter. Okay, so this is a arrangement in which this particular converter works for charging as well as you make it work for the propulsion mode. So here there are two separate converters, here also, here also, but in this case it is just a single unit of your converter that works for AC to DC and DC to AC. So this is what basically we are going to talk about all our discussion today, because I am going to explain you about this type of grid connected converter while making it charge. So you could see here onboard charger and offboard charger, a basic comparison. Onboard chargers mostly are having less capacity. Problem of battery heating is not concern. Weight on EV is added due to some filters which are been there, but they are also compensated for something better that we will see. Slow charging, charge at power levels, level 1 and 2. So not much of the power, but it is possible for us to build electrical vehicle of level 2. Even more than that also. Now with the new thing which I'm going to talk to you. Then size and weight restriction due to EV design. Similarly, if you see off-board charger, high energy transfer is feasible. Weight on EV is removed. Fast charging, charge at high power levels up to level 3 can be achieved. And no flexibility to recharge at various places, because if it is a DC point which is available to you for charger, then this type of thing will not work under off-board charger. So considering this one, let us look into a basic fundamental of integrated onboard charger. You could see here, there are two categories which are there. One is single phase and another is three phase. In this case of single phase, you could see here, grid is here. That's a single phase. LC filter is connected and AC to DC conversion takes place for charging. And there are three limbs, 1, 2, and 3. They are like a boost converter. So all these interleaved boost converter, they are connected together and DC generated. So this is what basically a charging that takes place here. But you will see that these particular inductors which are been there in this case, these inductors which are shown in the circle is nothing but a motor winding. Now you will see that I have used this inductor that is a part of our motor in our traction. So this three-phase winding, let us consider a three-phase motor. So these three stator winding which are having a star point from which I am feeding this DC here, and then it is being connected here to make this particular boost conversion. When you remove this particular point from here, disconnect this one, you find that this becomes a two-level three-phase inverter giving supply to the motor. Is it not? So if you disconnect this part in the propulsion mode, then motor will work. For charging, you connect this point and then you can charge it and battery can be charged here. So your interface of this particular part, that is between grid to this one, through this particular only single, this particular type of conversion that is been shown here on this side. But basically it is just simply interface. I will show you what exactly it is. Then there is something like another methodology in which single phase is connected at this 2 point, and then this is a motor 1 and motor 2, and between this motor 1 and motor 2 there is AC to DC converter on this side and AC to DC converter here, and they are parallel. So when you are charging that time, you will be converting your AC supply to DC here through again a boost type of conversion. And when you make a disconnection of this part, these two motors can work independently from the same DC bus. So this is about the single phase. For three phase, you could see here in three phase, this three phase grid is connected to the winding at the center point, wherein the motor is having a winding that is split. Split means this is one winding actually, but that is connected at this particular point. This is that point. So this is single phase which is there. Then there is an edge bridge connected to that one, and that will be connected to the DC. So you can get a conversion of this particular AC into DC through an edge bridge. And then if you disconnect this one, you can also make this particular inverter to build an AC voltage, so that this whole thing will not be there. It will be 3 windings which are being fed from each of this bridge. So you find that when you do this particular thing, there has to be a very important consideration. What is that consideration? You see here in propulsion mode, a total flux has to be a sinusoidal, which is to be generated inside this particular winding. But while charging, if you connect some supply and the current is flowing through this one, this will try to generate a flux that should not create any motoring action. If that generates a motoring action during charging, then that is not a correct way of making this particular charger to work. So while doing this one, this total flux should be 0. There should not be any flux. Otherwise, you will have another problem that is related to the mechanical system, because motor will start running, because stator winding only you are going to take into action. So while charging, we are using stator winding, but it will not create any torque. So the shaft of the motor will not rotate. That is the condition. And this particular condition we have to fulfill by 2 ways. One is by making an appropriate configuration of winding while charging. That is one. Second thing is, while doing this one, if there is going to be some kind of induction that takes place on the motor and interaction happens, whatever vibration that is going to be generated on the rotor side, you have to take care of that one. So these 2 considerations we have to look at, and we will try to see that first option should be best, because if that happens, then we will not be getting any torque generated during the charging. So same kind of a topology which is there, and you could see here what is been done. Typically it is like single phase, then line filter, and you could see these 3 phases which are connected to this inverter. This is 3 winding of a motor. When they are connected and battery is supplying, and under traction mode, this is open, and this will be closed. So all 3 phases are connected to the inverter, motor will run. But while charging, what you need to do is you need to see that these should be connected, and this should be open. So what will happen? You will see that this particular winding in series with this 2 will be connected to 2 legs here, and that will get you a boosting, and that will create a DC on this side. So we can make a charging arrangement by making this particular changeover that will happen, and that will get you this particular configuration. Similarly, here also you could see that there are 4 inverters which are being shown here, and this single phase AC supply will be converted into DC, and then this will be on the same bus. You can have these batteries to be charged through this inverter operating mode, which is to be controlled upon. So there are various topologies which can be built by us while making this interface to our electrical vehicle. So the problem is when you connect this one to your all these charging application, that time you will be utilizing this particular winding as a filter. So we see here that this plays an important role. When the motor is being considered as a part of filter, then you will have a very typical problems that you will encounter. In three-phase, you could see here, it is a PMSM motor, and in that one, it has been shown that three-phase inverter is having two windings which are been a part of the same stator. It's not different. It is same winding 1 and winding 2 which has been there in the stator for a phase R, Y, or A, B, C here, but they are split. They are split, which I have already indicated to you. While making this particular arrangement in charging mode, you see what happened. Winding 1 was star. This was made star, and another winding which has been there connected to the three-phase grid. So this whole winding is in the stator and they are now isolated. It is like a transformer action, primary winding and secondary winding. So you will be transferring power across these two transformer winding, and on this side there is a three-phase inverter which is connected to the battery. So while making a charging operation, you will have to build this, which is very easy. Externally you can do that one, so that you will be converting your this three-phase winding which is split into two separate winding in the stator of the machine, and you can do it. Similarly, for three-phase, you could see here that in another machine, this is one inverter, this is another inverter. There are all motor windings here. You could see here A1, B1, C1, A2, B2, C2, and both are connected to the grid from this side. If you do this one during charging, this DC bus which has been available, that has been connected in parallel. While making it to work in the traction operation, you open this one. If you open this one, these windings which are there, they are in the same motor stator connected in series, and hence two inverter on two end of this winding. It's open end winding kind of configuration for the similar kind of structure that could be also built. So as I told you that we have to play with stator winding in such a way that we should able to make use of our inverter to be connected to the grid appropriately through a proper filter, so that this interface gets you a better power quality, as well as a function of charging should be appropriately done. So this is three-phase. Earlier I have shown you single phase. Now we'll move to next. There is something like three things which you need to know about while designing such kind of charger. One is a galvanic isolation, then circulating current, and reconfiguration required. There are many things like type of motor, stator winding used as, supply, type of inverter, and this is what you can get from this particular arrangement. So you could see here, this has been compared and various references are available. And in that one, you find that there could be S for galvanic isolation, then no for circulating current, then reconfiguration required, which has been there. Yes, we need to do that one. You could see here it is no, no, no. That see here in this case, all these things are very important when you connect anything to the grid. And while doing that grid connection to an inverter, we have to be very careful, because in the today's grid, we are going to inject many of the new devices which are being used for our purpose, like batteries in electrical vehicle. So as you have just now seen, the configuration which is been there in this typical arrangement, you have seen this one. So there is a winding which is 3-phase only, series connected, but on both the end there is an inverter. Now, if I would like to make better and better use of such kind of configuration that could be available to me, so that I will be able to make this arrangement better for my charging purpose. So we are having an option for stator winding, in which we can build stator more than that of 3 phases. So here we have now a choice of multi-phase drive. I am little bit entering in the multi-phase drive, but it is essential to know that you get some advantage on account of charging process that is essential in electrical vehicle. Along with that, you get multiple advantages that is associated with multi-phase drive. So in such kind of thing, you find that 3-phase supply will be there, but we will be using motor with a multi-phase. So you will be in position to see that 6-phase induction motor, 9-phase induction motor, all these motors which are connected and used for, let us say, for charging purpose, wherein something like as what we have already seen, galvanic isolation, circulating current, and reconfiguration, if it is required, what kind of hardship we have to do, or what kind of circuitry we need to develop. So here I am going to just brush upon the importance of multi-phase motors. You could see here that this particular motors will have certain advantages like reduced power current rating per phase. Obviously, when the phases are increasing, current per phase will be reducing. It reduces the torque ripples, because instead of 3, it will be having 6. So you know, 5th and 7th torque ripple that is present in our 3-phase motor, wherein as you increases the number of phases, you find that will go multiple of number of phases. So it will be reduced with such kind of high frequency ripples that will be there. Lower DC link capacitance, that is another thing that will happen. Reduction in stator copper losses, because you find that a current per phase which we have to manage in the stator is less. So to some extent, it will be reducing. So it contributes into the increase in efficiency. And very important part here is fault tolerant. If 3-phase motor fails on one phase, it is we call a single phase. We will be having a trouble of delivering the torque. But in multi-phase motor, even one phase goes, still motor will continue to run and without much of the issue related to the overheating and so forth. So you will be able to generate torque also, you will be able to run that motor. So such kind of advantage you get in multi-phase motors. You could see here comparison of 3, 5-phase, 6-phase, 9-phase and 12-phase motors. Let us talk about a phase current in per unit. You'll see that per unit current falls down drastically, and ripple also, like 6, 5 and 7, I said it is ultimately making it 6, and then it is 12, 18, 24. Then copper loss reduction, you could see here, it is small reduction, but it is efficiency improvement that will happen. Requirement of DC capacitance, so you could see it is less than 50% than that of 3-phase. So there is certain saving on account of this one. However, there is also a cost which you have to pay for an inverter which requires 6-phase inverter. Instead of 3-phase inverter, is 6-phase inverter. But as earlier configuration of open-end winding I have shown you on in 3-phase, it requires 2 inverter. So it has a 6 legs. Similarly, if you consider 6-phase motor, probably you will be able to manage with the 2 3-phase inverters. So let us see what type of motors configuration of winding that is available to us. This is 2 3-phase winding which are overlapping on each other are 0 degree. Then if one winding is disposed by another, that is 60 degree, if they are having a 30 degrees phase shift, physical also they have to do this one in winding, that is 30 degrees. So these 2 categories are considered to be a symmetrical 0 degree and 60 degree, and this is asymmetrical. This is asymmetrical 30 degrees. So these are the 2 categories of 6-phase motor winding configuration. Then we are having some problem of 6-phase or multi-phase motor in pre-PWM era, because these machines were known earlier than that of power electronics comes to the really in industrial application, but we could not use this one. When you apply a 6-phase supply to these motors, you find that there will be certain distortion in current. These distortions in the current was then investigated to be on account of some subspaces, subharmonic spaces which are also generated when you go from 3-phase to 6-phase or 3-phase to 5-phase. When you go for higher phases more than that of 3-phase, you will have some another subspace harmonics that I will just explain you in the next slides. Before that one, what is basically when you look into this type of stator configuration of motor having 3-phase motor or 6-phase motor, what are the basic issues which we are going to sort out? Here we always talk about that, yes, electrical vehicle means we will be having a vehicle to grid operation also, grid to vehicle, that is a charging mode, and then propulsion mode. If you disconnect this part of your supply, then this becomes a complete system on its own, will work with the battery as an energy. So you have got a supply side then you will be using motor, induction motor. In this case, it could be PMSM, and this motor is connected to one inverter here having a DC link. This DC link is then another connected to another DC to DC bidirectional converter, which will be going to match the voltage of my battery, because this battery bus and this may not be same. Therefore, we have a DC to DC bidirectional converter. Both the converters are controlled by using appropriate algorithms of control which are required to be developed and implemented on the DSP. So you need to take certain signal as an input for our control. So we will be generally measuring a terminal side of a motor, that is a grid connected voltage and current, and then DC side battery voltage and current. So this is what a basic system will be there. But while building this system, we have to keep in mind that there are certain things which are important for all of us to understand. What is grid norms? If you are connecting some system like this one, you have to see that you should not inject any harmonic into the grid. So that's one part. Second thing is, it should be not loading for the reactive power which is to be taken from the grid. So you should always have a unity power factor on the grid side. I mean PCC, I will say that our inverter which is connected through this particular motor to the grid here. So this inverter and this grid is now getting connected through this particular, what we call it as a filter or inductor. So this particular whole thing that goes here is a interlink between the inverter and grid. So while doing this particular part, we have to see that while charging, you should not make this particular circuit to supply reactive power. It should always have an interface here getting you a unity power factor. Means voltage and current on this should be an unity power factor. So this particular criteria as a grid norms we should able to maintain. Then filter design, as just now I have told you, this inductor in the machine which is constituted as a part of our stator winding. This is very crucial to make this particular system to function. All of you know now that in the smart grids or the grids which are being connected, healthiness or operation of inverter really is a critical thing when you connect that to grid, which is having a critical component called a inductor in between. This has to be properly designed. So when we got a motor, we don't bother much except a stator impedances which you generally measure and do it according to the rating of a given machine. But when you consider that winding as a filter, then we have to look into much more detail whether that is going to be suitable for an application of grid connected chargers. And so we should able to look into a appropriate design, reconfiguration, and then work out. Of course, third point is control algorithm. When you talk about the control algorithm, I will say that when grid is connected to inverter on DC side, there could be certain DC oscillations which are been there. There could be a unbalancing on this side that has to be taken care. So we have to build really a good control on this side so that we should able to maintain a balanced system of current on this side. And of course, the last and important thing is cost effective and operating ease. Operating ease means as a reconfiguration which you require, it should not be a very complicated system. So cost effective and it could be operative very easily. It should be operatable by any of the person. So it should be that kind of system. So when you build with such criteria, you have to look into various aspects that we are going to present now. Yeah, so there are two things. We will bit quickly will make this one to propulsion mode is nothing but a motor that has to work for an electrical vehicle, has to work for a dynamics that is to be matched to the load. And what is a load on electrical vehicle? A passengers which are seating, then the torque that has to work on various frictions, and a road condition that is to be there. So we have to build a better control of our machine. I am focusing whole discussion with the induction motor, because we are going to show you about the actual work that has been done by us on induction motor. So we are having a very suitable and important control algorithm that suits to such application is called direct torque control, DTC. While doing this one, we have to look into the machine live while doing this one. So we have to get a CMV elimination, then there should not be distortion in current. So multi-phase machine, as I told you, there will get, if it is number of phases are more than 3, it will have unnecessarily harmonics, subspace harmonics we call it, that should be removed, which I will show you how they get generated. While doing with multi-phase, you have to take care of these things. In charging mode, we are working with integrated system that, as I have told you, then we will be going to look into only two aspects. One is how we should make during charging that rotor should not rotate. That is first. Second thing is, it should not create any losses on the rotor, because the charging current will be flowing through the stator. It will definitely induce something on a rotor that should not call for very heavy losses into the rotor. Otherwise, temperature rise will be there, and these losses will call for the degradation in efficiency. So you have to choose appropriate control algorithm to make it happen, along with a norms which are related to the grid to be followed. This is all related to a multi-phase system wherein it is now moving with the same basic control algorithms, but it requires something which very specifically I can say that it should be going to create a voltage vectors that are not going to generate the subspace harmonics. So how it is, that we'll see. Well, up till now I just summarized all the things to you, what way we should look for the propulsion as well as for the charging. So in electrical vehicle, when both are there, we have to see to it that how we could do best use of this type of system with the control algorithms which we can develop. I hope I am audible to all of you. Hello?
Yes, sir, you are audible, sir.
Okay, fine. Now, propulsion mode of electric vehicle. I will just briefly, because that is a type of drive system, but the focus is mostly on the grid side. Therefore, I will skip something which is related to detailing of propulsion that is related to electrical motor, induction motor. Here, symmetrical 6-phase machine model is being shown here, and you will find that there is like VD, VQ, all of us know. Those who are electrical engineers, they know that 3-phase system is equivalently represented by D and Q and 0. If it is balanced, 0 is not there, so therefore it is D and Q. But I have written 2 more equations. These 2 equations are shown here. This is VXS, VYS. This is what I told you, that they are subspace harmonics. If these voltage are there, it means there will be current flowing, and this current is influencing the DQ current, which calls for the distortion. Therefore, till the time power electronics was not there, these multi-phase motors were not used, because there is going to be a lot of distortion in the stator current, and that cause was because of this XY subspaces which are being available or they are generated. So we try to find out that how basic torque equation is going to be. Here it is a basic torque equation of 3-phase, which you could see here. You find that this voltage X and voltage Y, that is subspace harmonics, does not contribute into the torque production. Therefore, all control algorithms which we have to develop, they are same as that of your normal machine control algorithms which are being implemented, like vector control, direct torque control. Under one condition, you need to eliminate this X and Y component when you are implementing this technique or this technique. So I will just briefly go for that one, because that takes us to a new area then otherwise. So here is the basic model that remains same. Here I just wanted to explain you that what is that DQ and XY. You see here, these are the 6 phases which are been there. It is a 60-degree machine connected to the 6-leg 2-level inverter, and these are the voltage. This is a transformation matrix which has been written here, and you find that if you make this T60, that's a transposition, this is a matrix which has been used to make a VD, VQ, VX, VY. Of course, V0 and V0 is also there, but that is eliminated under the pretext of these windings are balanced. So you find that these 6 phases are equivalently made into a 6, but shown here 4. So Vx and Vy is always generated when you got 6 phases here, and that transformation is here. This is a transformation matrix which is there. When you have this transformation matrix from this one, this is what the constant which you are going to get is part transformation basically. So you get this voltage VD, VQ, Vx, Vy. All our torque production will be based on the VDU and VQ. This Vx and Vy are not taking part into any torque production. Only thing is they create these voltages at the terminal will draw current. This machine will draw current which is of different phase, and so it will call for distortion in the main current, so the harmonics. Therefore, we call them as a subspace harmonics. And while implementing any control strategy on this inverter, we have to eliminate this X and Y part. So here what you could see on this particular DQ subspace of voltages which are being generated. This is a 6-phase inverter, and this 6-phase inverter will generate 64 voltage vectors. You know, in 3-phase 2-level, it is 8, 2 raised to 3. Okay, there are 8 voltage vectors. 2 are 0 and 6 are active voltage vectors. So in this case, it is 64. In that, 10 are 0, 36 are small, 12 are medium voltage vector, and 6 are large. So whole thing is mapped and their position is been also fixed. So you could see here that this is large, small, this is medium. So this is a medium voltage vector, and they are placed properly with the appropriate location having a magnitude. This I think if you know SPWM, then you know this one. Otherwise, probably some of you might not be able to understand what this particular part is. If it is SPWM, in that one, we know there are voltage vectors which are 8 that we switched appropriately in such a way that we should get a very nice sinusoidal voltage. Of course, that will not be so, but the thing is, it will be to the possible best you can generate, and you will be able to build your inverter properly. Now you look into this part that is XY subspace. As I was talking to you that when DQ are generated, XY subspaces are also automatically generated. When the inverter is switched with this one, this will also generate. This will generate means they will map all the same 64 voltage vector here, but at different location. And then magnitude is also different. So they will be available and they will create, as I told you, a current that is not acceptable. So if we consider that part, then we'll have to look into something which is very critical in application of algorithm that is there. In simplicity, I will just talk to you on the direct torque control in just brief. This is just a torque which is proportional to the flux linkage of stator, rotor, and angle between them. If that is the case, then you could see here psi s, which has been there, and psi r is here. If you have got a inverter having, let us say, so many vectors at your disposal and apply for, if you can apply them for a delta t, then you could see that if you apply this voltage vector, I mean this is a position of psi s, and you apply this voltage vector, then next location will be V14 here. I mean, sorry, this is not V14. This is V14, but this is your V56. Okay. So if you add this one, this V psi s is nothing but integration of voltage. So this is what an integration of voltage, that is V56 into delta t. If you do this one, this is the next position of psi s, which will increase the sine angle, so the torque will increase. But little bit flux will also increase, because this flux is, suppose here, it should have been here. If this will trace circle, so this will be increased on little bit. But then there is a way of controlling that, and that control is called basically direct torque control. So I am going a bit quickly on this part. Here you could see here a control strategy in which you will be able to look at a torque comparators. This is a torque comparator, this is a flux comparator. So this is the logic which has been used in this comparator, and you build the direct torque control. So our intention is not to look into the drive side. We will be looking into a basically aspect of our grid, but by looking into a basic control that, as I told you, will create a best possible electrical vehicle that is being implemented with direct torque control. So we are having a choice of all these voltage vectors to be selected, and if you do that one, we will be able to make a very good direct torque control which gets you a reduction in the XY subspaces or elimination of subspaces. Then you can improve on the torque ripple, that is a bit disadvantage in the DTC, but in DTC now we can make use of a higher level of hysteresis controller, then we can eliminate that part also. CMV elimination in the motor, that is also there, so life of motor will increase. This is our experimental setup, and in that one we will see everything is here. It's a 6-phase inverter. Here, this is a 6-phase inverter. This is a one which has been shown here. It's 2-level 6-phase inverter. This is a 6-phase drive. This is the one I have shown you here. In two, a symmetrical 6-phase induction motor has been shown, right? But you could see there are two motors here, and one third is the eddy current brake. That is the brake on the induction motor. So these two motors, then there is one motor on this side also, and there are 3 motors which are connected to the common shaft. And you know what is these three motors? You have seen earlier I have shown the winding 0 degree, 60 degree, and 30 degree. So all 3 motors are available with us. We can experiment on any of the motor as what we want. And then this is a DSP and all further things which are being required for control. So you could see the result here, and if you look at a trace of stator flux here, a DQ subspace flux, and XY subspace flux. Here you could see by applying appropriate control algorithm, we could make a phase current almost sinusoidal, and we will be able to get a better current. Here there are some kind of distortions which are been there, that is in the our current which has been there with 5-level torque comparator. This is a 3-level torque comparator. We try to build some new algorithms wherein you could see that XY subspace in this 3-level torque comparator is almost 0, and here it is bit oscillatory, which is there. Well, 5-level torque comparator, which is further more improved, and it has come to 3-level comparator performance. You could see here XY subspace is 0. Well, there are comparison wherein the torque, speed, and all those things which have been tested upon in this machine, that has been shown. We are not looking into all this particular part as far as our machine is concerned. Here it is with 60 degrees with appropriate selection. We will be able to make very important contribution, that is elimination of CMV. That's a common mode voltage in the given machine when you work with such kind of inverter. And that is about the 3-level torque controller, 5-level torque controller, then modified torque controller, then modified torque controller, which is 3-level and 5-level, and then we could see a comparison of torque ripples and also and so. So that is a comparison, but this is the machine performance side. Well, this is about the machine. We will not be much of interest, but I just wanted to show you because there's a direct torque control that applies supposed to this part. We will be having a much better performance of EV. Now look into a charging mode of electrical. In charging mode of electrical vehicle, I'm going to present to you a 6-phase machine. In 6-phase machine, there are such kind of winding. 6-phase 0 degree. You have seen earlier 3-phase with 2 windings in the stator. I told you that they are series connected, but there is a tab in between. Here, the case 1 looks to be like that. So there are 2 windings in 6-phase. Here one RYB, here R dash YY dash B. Now these will be 3 terminals here, and these 3 terminals which are on this side and 3 terminals on this side, if they are available to you, so you will be having 12 terminals. If these 12 terminals are connected as a case 2, you could see here they are connected in series. Here it is series, and then again there is a cross here. Here it is again series, but a cross here. So it is this particular part we are talking about 0-degree induction motor, because that is based among the 30 degrees and 60 degrees for the purpose of grid connect. Okay, so case 1 is a normal motor when they connected here in series like this one. A standard 6-phase motor will be look like there. I mean, there will be 2 star, sorry, here, and 6-phase will be built, because this particular points will be connected here in this case. So you will be having this 2 star, that is with the 60 degrees, 0 degrees 6-phase motor I'm talking about. Now here the case 1 is this one, case 2 is this one, you see here, and case 3 is here. So if you see case 1, a normal motor will generate a rotating flux as what it is being shown. But as you make a case 3, what happens? You just see here. It is a pulsating torque. This is all analysis done in ANSYS by us, and we found where is going to be a location of our flux. So you find that in case 3, it is generating pulsating torque, or pulsating flux. If this is the case, then in this case, case 1, if you supply these 6 phases as what I told you, 3 phases on this side, 3 phases on this side, then you will be getting rotating such flux, creating a rotor to rotate. But if it is a pulsating torque like this one, it is at only one position, you find that it is not going to make any torque production. So our work can be done. And therefore, we will have to choose case 3. That will be better option. We have to analyze this also. You'll find that there will be some modification in this rotating flux. And under these circumstances, if you measure the parameters of induction motor, you will be finding that, as let us take case 3, equivalent resistance and equivalent inductance, which is being shown here, you could find that if the windings are mostly series connected, then this is what it will be, and equivalent inductance will be of this value. And if they are parallel, this is what it will be. Why I'm showing you this one? If machine stator phase impedances are not balanced, then motor will draw different current. Is it not? It is unbalanced current. And that is going to be a problem when you have a pulsating magnetic field, that is in case 3, will have unbalance in this particular impedances, creating trouble for us. When you start charging, you connect this motor in charging mode, you will find that the currents are not balanced, and hence it reflects on something else on the DC side, on which you are going to connect your batteries. So the challenge comes here, that how to make this current balance, even the impedances may be not balanced. And we find that these inductance values or whatever impedance values which are there as compared to case 2 or case 4, you see that you get a better value of your impedances in case 3. And that is what a requirement of filter means. It has to even satisfy the required design value of filter inductance, so that this will work better when you connect grid. And now if you look for a case 3, which is just as earlier I have shown to you, here you see here these windings, how they are connected. One single one is straightforward, but this is all crossed. Here it is same windings which are been there, but they are connected parallelly. Instead of series, it's parallel, but impedance will change then. So both things are feasible. Which one is better, that we will be able to look at when the results are presented to you. Here is our basically 6-phase integration with the grid. On this side, there is a 3-phase which are connected to this particular machine, 6-phase machine, in which we are in position to get these two things, that is RS1 and RS2, as a reconfigurable contactors which could build this particular circuit. And all this one is connected to the 6-phase converter, and then that DC which has been there, that DC is furthermore controlled to requirement of battery. Means it could be step down voltage. So in this case, when you make this particular machine winding, that as I have shown you earlier, series or parallel, you take an help of these contactors, so that we'll be able to make this arrangement as what you want. When you disconnect your grid supply and run this particular machine as a 6-phase machine in DTC mode, you control this particular inverter in DTC control and run as a electrical vehicle. So during charging, the configuration which has been required, that we have seen just now, and we are having two challenges. What are those? Those are basically unbalanced impedances of stator, which calls for the unbalance in current. That is what it is. And second thing is whether the value of this particular impedance is going to be a required value for a purpose of connecting inverter to the grid. And while doing this one, you need to maintain a power quality aspect on grid side. So we have got 3-4 things, like we try to run this machine with the charging. Under charging, this should have a unity power factor. There should not be any oscillatory thing, DC oscillations on your DC bus. You should not have any problem of making these impedances low, so that you will be creating a trouble in operation of your inverter. While working as a motor, this will be disconnected, and 6-phase motor, the 6-phase motor will run with the 6-phase inverter. So while charging also, you will get a better ripples content here. Better means, I mean to say, there are parallel paths. Each of them will be acting like a boost converter, and they will be like interleaved type of converter, wherein multiple interleaving will reduce the ripple that will happen. So all these challenges which we have to take care by building a control around it. Let us see a simple one in this fashion. I mean, this is what you could see, that if it is to be a charging operation, in charging operation, all 6 legs are not going to be used. If you look into this one, charging mode, RS1 connected to 2 terminal and RS2 is open. If this RS2 is open, then this will be only using 3 legs of this particular converter, and that is what a charging operating mode it will be having. But problem is with this particular impedances which we are going to use with, because criteria is, while the currents when they are flowing in this particular winding, let us on this direction, it should not create on the rotor. This rotor is free. This rotor should not rotate while charging. So under pulsating torque, you have to choose the winding configuration that is 3, and you will see that that will create unbalances in the current, and hence we have to look into that part. We have built a control scheme for that one to maintain the balances in the current and removing the oscillation on DC grid, wherein we have used decoupled sequence extraction block and double synchronous reference frame controller. So we should able to maintain the balance of our current, as well as making it possible for us to do away with any of a what I say, a double oscillations which are been there on the DC side. So we could achieve that part. Of course, this system remains as what I have earlier shown to you, and we will be just looking for certain experimental result which we are going to discuss. You could see here these 3 currents are not balanced, are grid currents they are, and you could see that THD is very high and there is no compensation for case 3, and you could see without compensation we have got all this converted current of direct and quadrature axis currents which are being extracted from the measurement, and they are having something which is not correct, because you see that if it consists of a reactive component, then you will find that your IDG should be 0, not IDG, this IQG should be almost 0. So you find that this is what it has been achieved under the compensating algorithm that has been executed by us. So our control aspect will be able to make it happen, and we are going to achieve here. See here, these 3 currents which are shown after compensation for the case 3, current R, Y, and B. These are all looks to be same, and this is the grid voltage, and you could see here it is maintaining UPF, unity power factor. This unity power factor is also achieved. We are able to maintain the grid current balance, and the THD part of that also got reduced. So quality of our interconnected onboard charger using induction motor winding as a filter is working properly. However, somebody will definitely object that a THD is still to be improved upon, but still you could see that drastically it has improved a lot. So we have achieved three things. One is sinusoidal nature, almost, unity power factor, and this is a DC. So you will see that this DC is almost within the given tolerances, much of the oscillations which are not been there. So we could execute that one, and we are in position to see that in series connection of group 3 type of winding, the results which I have already talked about. Similarly, when we use parallel combination of case 3 winding, obviously the impedances which are being shown to you in the table were less. Therefore, you find that a lot of such kind of spiky currents are flowing without compensation. Without compensation, the spiky current which are being flowing, and THD is very, very high. Without compensation, the currents are shown here. After compensation, you could see that IDG is properly there, others are gone to zero. So here also we could make a possible agreement of what we are expected to do. And in this one, you find that they are balanced, but it is not, it is still having a lot of high frequency ripples. However, unity power factor is achieved. THD has not reduced much. We are in case 3 parallel winding, right? And VDC is almost maintained. So in both the cases we have shown, but we wanted to compare whether in parallel with the lower values of impedances, is it possible for us to make a controller to work for getting us a proper grid connection? Actually, this is having a norm on grid side. You can't make an onboard charger without maintaining a power factor unity, a less harmonics contained into it. So you have to appropriately do this one, because we are not adding any extra additional impedances in that one. If we try to put filter there, definitely electrical vehicle is not going to be very justified on account of its volume that you have to accommodate, weight you have to accommodate. That is done with it, because that is not required when you take an impedance of a stator of motor winding. That is the advantage of this particular type of scheme. We have obtained the losses in the filter, then efficiency. Losses in the filter means, as I was talking to you, there's going to be a pulsating field which has been generated under this particular circumstances, which calls for a heating on rotor. That losses will be there. That losses we have to add into our complete efficiency, and hence we have added that one, and we could find that efficiency which has been contributed by these losses, considering a parallel and series connection that is being shown here. So all these details are there that I will refer to you with at the end. Well, in 6-phase, you could see here that the configuration which I have shown to you is externally managed also by having a phase transposition that has been done in symmetrical motor like this one. You see here, these 3-phase grid, then there are 2 isolation transformer, Y, and then these are disposed, so this is all transposed, and then this is 6-phase machine that is showing you here a integration of inductances to the grid. So this is inverter, then battery will be on this side, other system will be here, but this is what it will be, a onboard charging which will be there. Now here this is what it is being shown as a transformers which are having a phase shift, that is with YY, maybe 0 degree you can have or 60 degree you can have. Here it is a asymmetrical machine. Of course, this is having a 30 degrees angle, so you will be making this transposition and connecting this motor here, and you can work on this particular part. So as I have told you that we are going to have a 6-phase machine which is to be run and shown here with the 6 phases which have been utilized here. But have you seen what topology I have talked to you? That does not have such kind of thing. Here in charging mode, it looks like a 3-phase inverter that has been connected, and in your propulsion mode, 6-phase will be working. So this 3-phase is connected. We didn't require 6-phase as I have shown you here. So that's an additional cost which this type of configuration, if you make, then this transformer will be, but it is an isolation type of system. So circulation current and other issues also could be managed, but it is isolated system. So, well, this will have a more of investment that is not justified as such. So how you can decide and how we can make the use of such kind of system that works for us? It depends on number of machine phases. It's not 6-phase only today. We are going to have motors which are having 5 phases, which are having 9 phases, which can have 15 phases. So you can use this type of number of phases more with its inherent reliable operating advantage. If you do this one, you need to manage your inverter and your charging system appropriately. But difficulty is your control algorithm, which I have shown for 6-phase, wherein the balances of the current requires has to be done thoroughly, then and then this will happen. Otherwise, it is a very difficult task for managing this type of thing with multi-phase. Type of supply, it could be single phase or 3-phase. Surely it is depending on the type of charger. If it is low power charger, and if it is electrical vehicle with, let us say, car, maybe you will have a single phase with higher power rating that can be done. I have missed one point here. As in our scheme, which I have shown you, wherein we could do this particular series parallel combination of our motor winding, which is connected to the grid, is going to make use of this particular type of scheme for type 3. It can enhance its power rating, because on charging side I am having multiple parallel legs of my converter that will distribute the current for the battery which it is drawing. That will be huge. So that advantage I can take of multi-phase, and so I can make use of this type of charger for higher power. So it is essentially that number of converter legs will be higher. Definitely we have to manage here. On one account, motor will give more reliable operation, and inverter definitely will have more number of components, but you find that their thermal stress is quite low, because per phase current that is a inverter component current per flowing at the rated value of motor is less. So you are not stressing your switches to very high currents. So the losses and other thing can be contained with. Charging with zero torque production, as I have given you an idea that pulsating torque that has been produced, if you could make some other arrangement wherein there is no possibility of generating any flux during the charging process, nothing like it. So there are various other technique or ideas which can be tried upon. Pulsating torque, as I told you, pulsating torque, that is another part while doing this particular charging business. If it is there existing, there could be some vibration that will be there. This vibration, if it is going to be beyond certain limit, then we will be having a problem of meeting the standard for the electrical vehicle. So we have to see that this pulsating torque should be contained with, and we have to maybe providing some additional braking or vibrating diminishing devices along with it. Then charging power to propulsion power hardware reconfiguration needed. This you have seen that 6 phases will be converted into 3 phases while it is charging. So this particular thing requires external contactors, which I have shown you, RS1, RS2. So these two things are external, and this is to be managed while doing this particular kind of conversion. Then in this case, V2G is also feasible, that is vehicle to grid, because you can utilize a grid connection that is possible through an inverter, and that is one of the good advantage you can have. Galvanic isolation also can be achieved if you properly make a connection and do it. So in summary, stator winding of induction machine used as an interfacing filter between grid and converter. So that has been proved that our motor itself works for the filter. Pulsating field is incapable of developing the electromagnetic torque in rotor. So we get an advantage, and hence do not require any brake or any mechanical thing to brake at the time of charging, because rotor is free, it does not rotate. Rotor is in standstill position without using the mechanical brake. That's what I was talking to you. But it creates a equivalent inductances of stator winding that is not balanced. But we can implement them by having appropriate control so that it could be executed and worked out. In conclusion, that well, DTC with appropriate technological advantage that is inbuilt in DTC executed with electrical vehicle life of motor, that is going to be more or better. With multi-phase, it is going to have a more reliable operation. So this is preferred. That's why I have taken this particular part in between. But in detail, it is a bit difficult in given time to explain to you. Probably that is not understood. We will talk about it later on. But charging mode, I definitely like to see that in the smart grid, we talk about too much, but when the power quality and the norms which are to be within the limits or to be followed strictly, under that consideration, we have to see that how to design this particular inductor that should be built in the motor stator winding, probably some motor winding modification, that is redesigning of motor has to be done in electrical vehicle, so that we will be able to make use of the stator of this particular motor to be well operational with the given grid. So that is what it gives you. Then unity power factor is another thing which we could achieve in this control algorithm. While doing this particular execution of control algorithm, which gets you an unity power factor on grid side, certainly sort out much of your stress on account of power quality norms to be followed with. Because if it is unity power factor, definitely whatever load you are looking for in electrical vehicle for a charging, it is nothing but a resistive load from the grid side. So this is very advantageous control algorithm which has been developed by us on the given machines which are with us in the lab. Well, anybody wants to refer anything related to what I have talked about? We are having so many IIT and IIII transaction papers on this particular topic. You can look into that one and we can discuss with them. So I think I have violated time norms of by 10 to 15 minutes. And this is what basically a future which looks like that in our country, probably cross diagonal, I should say that we will have electrical vehicle. It's with a simple and best transportation device or vehicle, that is three-wheeler, you could see here. And across that one, there is a Tata Nexon that has been there, having a charging that goes with this machine or this particular vehicle. And other two are crossed purposely, you know. So see, I was talking about the grid connection, but now it is a solar which is to be connected to this particular electrical vehicle. So there is a DC input now, which is going to be there. And if you want to integrate DC, still you can do it in the given configuration. So you could see here that if the solar panels tomorrow you are going to have, you want it should not be connected with the grid, then there could be a possibility of doing that also in the given electrical vehicle. Across this, you could see in this one there is a petrol pump. Beside that, there is a electrical charging station. The future is not far. In our country also, we will be able to see such kind of thing. So thank you very much, Mohan. I am going to end here. So
Yes.
yeah, now thank you very much.
Okay. Thank you, sir, for your wonderful session on power quality issues in onboard grid charging for electrical vehicle. Just reminder for participant, please be sure to type your question into the question box in your control panel. Sir, one question is there. It is possible to power generators to produce or fulfill a requirement for electrical vehicle.
Power generator, can you repeat please?
Is it possible to power generators to produce or fulfill requirement for electrical vehicle? Because nowadays we cannot fulfill the power requirement for normal users.
Yeah. It's going to increase the load on our grid. That is the first and foremost thing. Because of electrical vehicle, when it comes, the energy which is saved on our petrol, diesel and all that one, but that energy has to be consumed through coal via generators, and hence our electrical vehicles will run. Prima facie, it is a bit difficult for us to have a directly increase in the load of our electrical vehicle on the present grid. However, alternative ways are like, as I have shown in the last slide, cross. That is, yes. PV panels which are there, that will be local PV panels generating this particular power, and still electrical vehicles could be powered. And in case if this power is excess, it could be it could be given back to the grid. So it is going to be really a very long-term planning and an appropriate redesigning of our present grid, so that we can accommodate this increase in the volume of electrical vehicles wherein they require the electrical charge, because petrol will go down. For example, if you go, it goes down by, let us say, 30% in consumption, but 30% energy is equivalent required from the grid, is it not? So therefore, we have to see that how this could be planned properly, and therefore there is a categorization first, and then according to that categorization we have to work out with the grid.
Yes. Great, sir.
Right.
Thank you, everyone. We appreciate you being here. One announcement is here. Tomorrow's session, first session will start sharp 12 noon. The topic of tomorrow's session is conditioning monitoring of power system component, presented by Dr. M.S. Balal, VNIT, Nagpur. And sharp second session will start at 3 p.m. Topic is voltage source inverter and its control, presented by Dr. Mohan Renge, sir. Okay, thank you, sir. It was very wonderful presentation. And once again, thank you for joining and look forward another session.
Thank you very much.
Thank you.
Thank you.
Thank you, sir.
Right.
Thank you.